can write nucleophilic substitution as a heading. Nucleophilic substitution. And hopefully everything that I cover here will be all you need to know for the IB. But there's kind of two parts to it. This lesson's going to be in two parts. There's this lesson, I'll teach you the most of the basics. And there's going to be another lesson where I'm going to go back to some stuff on isomers. And then I'm going to come back to SN1 and SN2, the stuff we're doing today, again in a future lesson. So subheading, if you like, is SN1 and SN2, and I'm going to go through each of those in turn. So I'm going to just sort of do a general thing to start with, the standard level stuff that I didn't teach you, or don't think I bothered teaching you when we did standard level, because I knew that I was going to be doing it properly now. So if I was just teaching you as a standard level class, I would have covered this, but I wasn't. So the nucleophilic substitution is substitution with a nucleophile. Complicated, isn't it, chemistry? Right, so as an example of that, we've got this molecule, chloroethane, and that can react with a nucleophile. And the nucleophile here is a hydroxide, but I'm going to draw the overall reaction with the sodium. Now, just for a little reminder at this point, that whenever we draw mechanisms, we don't show these spectator ions, these counter ions, okay? So, and some of you did in the mock or in papers that I've seen you do for me. Some people have attempted always to draw the sodiums, the counter ions. You don't, that's an OH. So what's happened there is the chlorine has been substituted with a hydroxide, okay? And you'll see if you look in the spec, there's a kind of little bit about what's going on in there, but not very much. So what we've got there is we've got a nucleophile, which is the hydroxide, and we'll talk about what that means and how we can identify that in a minute. It's a bit blurred, isn't it? Let's see if we can unblur it. And we've got chloroethane as the substrate, and you can see hopefully there's a delta plus, delta minus there. How would we know that that bond is polar and what that polarity is that way round? Have a little discussion about that for a minute. Right, so nucleophiles are things that, as you said, like positive charges, so you can get negative nucleophiles, but you can also get neutral nucleophiles. And so it's just as a little aside here, I'll just stick it in the margin, you can get neutral nucleophiles like NH3 and H2O. And they're nucleophilic because they've got a lone pair that can do that attacking. So these are neutral nucleophiles. Right? And there's two lone pairs on oxygen, of course. Which is more nucleophilic though, water or hydroxide? Well, that's an easy question which often is asked and gets, get 2 marks sometimes. Well, which one likes positive charges more? Well, hydroxide does because it's negatively charged. Negatively charged things like positively charged things. So hydroxide is the nucleophile. Chlorine is the chloroethane is the substrate. The leaving group is chloride. So the thing that's lost is the leaving group. And we'll talk about leaving group ability to a certain extent when we get back to it in the second part of this in another lesson. But we talk about the things that affect the rate of these reactions. So chloride is a leaving group there, and that combines up with the chloride. So the mechanism of that reaction, we're now going to focus specifically on SN1 for chloroethane. And the mechanism I'm doing for SN1 applies to all primary halogenoalkanes. Right, this is primary halogenoalkane. Why is it primary? Again, I was really picky about this earlier on with the other group, and picky with you guys as well. Evie, why is this? Right. As I was in the pause of discussing whether this is primary, secondary, and so on, I realised embarrassingly that I'd put that as SN1 and it was SN2. So if you change it to SN2, this is a really important point. Okay. So SN2 is the mechanism we get for all primary halogenoalkanes, and we need to know that it's a one-step mechanism And we ought to know that what the SN1 and SN2 stand for. So we'll do that, I'll write that down underneath after I've drawn the mechanism. Right? So the reaction, first of all, is that the hydroxide reacts with the halogenoalkane. This is the same as what we wrote before, to give the alcohol and the leaving group Cl-, which, as I said before, would have combined to give sodium chloride, but we don't need to draw it in the mechanism. Right? So that's essentially the mechanism, or the reaction, sorry, but the mechanism involves the nucleophile, and particularly the lone pair on that nucleophile, attacking that delta positive carbon. Remember that double-headed arrows show the movement of 2 electrons and show the formation of a bond between that oxygen and that carbon. Right? So carbons can make 4 bonds. And so if I try to make a bond between that oxygen and that carbon, I've got a problem. I've now got 5 bonds. So something has to give, and the thing that gives is the carbon-chlorine bond, and that breaks. So we draw an arrow from the centre of that carbon-chlorine bond onto the chlorine to make a chloride. This chlorine becomes negatively charged because that was 2 electrons, one of which belonged to the original chlorine atom, if you like, and one of them has been given to the chlorine atom, making it now negatively charged. So there we go. So then we've got, that's the one-step mechanism. But we need to know how to draw something called the transition state. And the transition state will look something like this. So I'd probably just wait before you start drawing, and then draw it once it's complete. So there's the carbon that's being attacked. I always draw that in the centre of the transition state. And then I draw the things that are coming off it that aren't changing. So the 2 hydrogens above and below, and this CH3 in this case. So I'm going to draw the CH3 up here. And I'm going to draw the H there and the H there. It doesn't matter which way around you draw them at all. It's irrelevant. The bond that's breaking, I tend to draw on the right-hand side. I try to draw it longer because it's breaking. And the bond that's forming is the bond between carbon and oxygen. So you're showing the formation and the breaking in a simultaneous, concerted approach. The word concerted is in the concerted, in other words, all happening at the same time, is in the specification. And that transition state is negatively charged because you're taking a negatively charged thing and a neutral thing and sticking them together. This thing doesn't exist. It does form for a fraction of a second. I mean, a tiny, tiny fraction of a second, so you can't even detect it. We know it's there because of a whole load of evidence that I'm going to be unable to share it, given limited time with you fully. But there's lots of evidence to say that this thing exists, okay, for a moment of time. But it's all one concerted step. It all happens in one go. And in fact, because it's one step, this step must be the rate determining step. Are you comfortable with RDS, rate determining step? Remember that from the rate stuff, or slow step. Okay, because there's only one of them. So that's the mechanism you need to learn for that reaction. It's not overly complicated. One step, and it's SN2, and what that means, it means substitution, fine. Substitution means swapping, just like a sports player being swapped for another sports player. N stands for nucleophilic, and the N is subscript. And the 2 means it's bimolecular. And you might remember, though you might not, that bimolecular means there are 2 species, 2 things, if you like, in the rate, or that come together in the rate determining step. And I don't know if you remember how badly you did on the rates question in your mock, but everyone kind of forgot how to write rate equations. Right, the clue is that if it's a rate equation, it's going to have the word rate in, and it's an equation, so it's going to have the equal sign in, which loads of you didn't bother drawing. And you also have a rate constant as well, and then the 2 things that are reacting, so CH3, CH2, Cl, and the other thing that's reacting, So that's the rate equation, and you're expected to know the rate equation for SN1 and SN2 reactions. I'm not telling anything, I'm going to tell you very little that you don't need to know. I might tell you a couple of bits that I get excited about. So bimolecular just means second order overall. That's what bimolecular means in rate equation. So there's two things come together in the rate equation. Okay, bimolecular. Have you heard the term bimolecular before? Did I use that when we were doing? So you know the overall rate of the overall order of reaction was either 1 or 2 or 3 or sometimes 4. So unimolecular, bimolecular, whatever, trimolecular. Okay. And I've already said it, but I'll emphasise the point that primary haloalkanes always react via SN2. Always, and you have to know that, you have to learn that. Now, if you could all make another molymod, so could you make a hydrogen attached to an oxygen and then have a second bond coming out of the oxygen? Can't read it. Don't worry. Descants for Christmas, it's like. Yeah. And then someone throw me there chloroethane, and someone throw me an OH as well, please. That fizz to my face. And then, come on, chuck us that, Connie. That's it. Right, there we go. There's someone else. That's horrible. It's got a 5 bonded carbon there. Not you. It's the carbon you chose in the box. It's not tetrahedral. It's got. But I'll need it in a minute. So don't worry. We'll finally learn when we need those. Right. So there we go. So that's what you've got. You've got the halogenoalkane there, and the mechanism. I kind of want you to know what's going on quite well here. So what's going on is that hydroxide is attacking that carbon, and it attacks it from the opposite side to the carbon-chlorine bond. And you can see, hopefully, that that bond is forming, and that bond is simultaneously breaking. So you end up with that going on, right? So when it's like that, bond angle, 3, 2, 1. 3, bond angle, it's a number, Louis. 3, 2, 1. Ooh, bond angle, 109.5, right? Shape? Hybridization? Learn them, eh? Learn them. They're not going to go away. You're going to need to know them. But when this bond is forming and this bond is breaking, check us that other one. Check us your one. Such aggression in that one. Here's what I think about chemistry. Right, this is perfect because this is showing. This is why the 5 bonded ones exist. It's almost like that. That's the transition state. So the carbon-oxygen bond is being made at the same time as the carbon-chlorine bond is breaking. But look at the shape now. It's not sp4 hybridized or something. It's neither one nor the other. But it's causing the shape to change. And that becomes quite important when we come back to it next time. So I want you to know a little bit. I'll just hold it up here. Is it better like that? Can you, there, how's that? The point is I want to show you that the things that don't change, the 2 hydrogens and the CH3, do not change at all, do not move, and they are now planar. And the other 2 are 180 degrees from each other. That's the point I want to raise, and you'll see why in a bit. Okay, so that's what's kind of going on there. Can you all show me by? No, that's yours. By just sort of showing how your hydroxide attacks your chloro. It's got a bit wrong. You'll be able to fix it. Sort it out.
So the chloro is not the gas level.
Right. Those days are gone, Louis. All right. I'm just going to pause and show you some extra stuff on the board. Okay, so we're going to look at SN1 now, and this is substitution nucleophilic unimolecular. And this is what happens when you have a tertiary halogenoalkane. And the rate equation, if it's unimolecular, must only have one thing in it, and we'll see in a minute that that is the halogenoalkane we're using, which is this tertiary one. And that's tertiary because the carbon the chlorine is attached to, I'll actually write this out. The carbon that the chlorine is attached to 3 other carbons. So let's draw that out fully. This will be a little bit of a pain to draw, but we're going to draw it fully, the first time at least. So again, that's delta positive, that's delta negative, react it with the hydroxide, and you end up with when you're drawing these, be so careful to draw the hydrogens. They'll knock a mark off if you forget one. Same leaving group. Make sure the leaving group is a Cl minus, and but a different mechanism takes place for this one. It's actually a two-step reaction. So the 1 and the 2 are confusing for people. The 1 tells you it's unimolecular, but it's two-step. And the 2 on the previous page told you that it was bimolecular, but that means it's one step. So you have to realise when you're revising that that can throw people off a little bit. So be careful with that. Right. The mechanism here is a bit different. So I'm going to show you on paper to start with, so we've got some notes, then I'll show you with the monomods, and I'll show you a couple of animations and so on. But I'll just wait for you to catch up. Are we kind of nearly there? I'll just wait a second for you to catch up. I'll pause this for a minute. So, very, very briefly then. So for you don't need to know this now, but just to show you a little tiny bit of extra detail. If we've got a halogenoalkane like that one, you know that that's a sigma bond. It would look something like that, right? But for every bond, for every bonding orbital, there's an anti-bonding orbital, and that anti-bonding orbital points out there. And if you put electrons in the anti-bonding orbital, it causes that to break. So we haven't. Yeah. So there's an anti-bonding orbital exactly 180 degrees away from the bonding orbital. So that negative charge, the hydroxide, has to dump its 2 electrons into the anti-bonding orbital for it to work. So that's why when you've got a tertiary one, it can't get to that anti-bonding orbital. It just can't get to it. So that's beyond the scope of the course, but it helps you maybe to understand why things go as they do. Right. So what is the mechanism then? And I guess I'll add a couple of details in another lesson. But the first thing is, the first step is that carbon-chlorine bond breaking. It kind of does so spontaneously. Now it is, as always with these things, there's a little bit more to it than that. And why does that happen? I kind of like to think of it, don't write it as an equilibrium, but kind of think of it as an equilibrium between those two situations. The carbon-chlorine bond having fallen off, making a chloride, and they do hang out kind of near each other, but they're no longer sort of physically bonded, touching each other. And so you've got this thing, which you've seen these before. So what's this an example of? it's a cation, right? That's on a carbon. So what do we call one of those? Well done. Carbocation. So carbocation forms, and then the second stage, so the first step, this is the slow or rate determining step. And the second step of the reaction is the hydroxide, lone pair going into there. So that's the second step, which is fast, and you end up forming the alcohol, the tertiary alcohol. Okay. And there's two reasons for it, only one of which I'll talk about today, which is that the hydroxide simply can't get to the carbon in the same way. So it has to be that the chlorine falls off, and then the carbocation that's formed is attacked by the hydroxide. Okay. Right. So write the rate equation. Okay. So I want you to draw energy profile diagrams for these. I'm just going to make a note to myself to cover something else. I'm going to just mention something else now, which I forgot to mention in the other groups. I'm just making a note to myself. This carbocation, that's formed is somewhat stabilised. Do you remember that carbocations are more stable? When we did all the Markovnikov stuff with alkenes, well, you might or might not remember, but when we do carbocations before, and if you've not remembered the mechanisms today, don't worry, we'll do lots of practice before I test you on it. But the carbocations I taught you were more stable if they're surrounded by electron-releasing alkyl groups. This is what we talked about, a positive inductive effect. That's true here. So the reason this can fall off and leave this exposed carbocation is because it's tertiary, because you've got this inductive effect with the three surrounding alkyl groups pushing electron density towards it. So the energy profile diagrams of those two mechanisms, we've got the SN2, which we did first, would look very much like reaction profiles you've seen before. So reactants and products, you've got the energy, what do you call this, reaction, progress of reaction. What goes on the vertical axis, Oscar? What goes on the vertical axis? Yeah. Looks like that, and you have activation energy here. And that's the energy required to break that bond, if you like. But the energy, so the transition state is at that point there. That transition state that we drew on the previous page that you've got to practice and learn how to draw is at that position there. But it's a one-step mechanism. The SN1 mechanism that we've just drawn has got a different profile. We've got the reactants and the products again, but we've kind of got two steps. So we show both of those steps. And then instead of there being something that doesn't exist for any length of time, we form an intermediate which exists for a short amount of time, and that's here. So this is where the carbocation intermediate is. There's the activation energy, or sometimes called EA1 because it's the first step to it, but it's fine for today. And we've got the products down there. Okay. So it's slightly different. We've got the carbocation intermediate in the middle there, showing the two steps. And the second stage has a second activation energy. Okay. I'm going to pause. So the videos, the animations are helpful. I recommend looking at them. But we do need to just make sure we understand the difference between, or the bond breaking for both of these mechanisms heterolytic fission. And when I put this to the other group, people have forgotten the difference between homolytic and heterolytic. So I'll just remind you of that now. So if we've got bond breaking going on, with a double-headed arrow, it's heterolytic. We end up there with R plus and Cl minus, for example. Movement of 2 electrons. But homolytic fission, you all know the example I'll use. It'll be a halogen. Single-headed arrows where we get 2 of the same thing, hence the homo bit of it. So we end up with that. So make sure you know the difference between those 2 things. I think I've covered everything that I wanted to cover with you today. So what I'm going to get you to do is we'll practice that. There's a few things I haven't covered yet. There's a few details I know I haven't covered. I haven't intended to cover yet. We can just practice that for a little bit, and then I'm going to show you some stuff on chirality next time, and then we'll come back to these with some extra details. All right.